Good day. I'm Jesus Guerrero from Tecnológico de Monterrey, joined by Daniela Diego, Nathan Simber, and Dr. Orta Martinez. Today, we present Aquabotics, remotely operated underwater vehicle for monitoring marine environments, or open source, low cost robot built on Rust 2 for real time environmental sensing or motivation. Coral reef and coastal ecosystem are under severe threat from runoff, warming, and acidification, compromising biodiversity, fisheries, and shoreline protections. Traditional monitoring, both surveys, fixed sensors arrays, and high-end subsea vehicles is expensive, laborious, and especially limited. We saw an urgent we saw an urgent need for affordable model platform that delivers real-time and data and can be eventually deploy remediation payloads. Our key contributions are a total build cost about $500 using off the shelf parts and 3D printing components. Second one, a waterproof polycarbonate hull with aluminum end caps and epoxy sealed cable penetrators. A Rust 2 and micro-ROS teleoperation change from Xbox gamepad to a SP32. And the last one, integrated sensing that extreme temperature and pressure over a Rust 2 topic. Under the hood, Aquabotics carries six waterproof thrusters driven by three dual motor drivers, and it has a pressure sensor, IMU, and a pexi cam, all mounted in two stackable breadboards inside a clear polycarbonate cylinder. Power comes from a 14.8 voltage Lion batteries, stepping down to a 10, 6.4, and 5 voltage rails by voltage regulators. With a with a 10 amperes slow blow fuse and waterproof switch assembling a custom PCB. The main idea of the servo control is use the values obtained from the Xbox gamepad and use these values to calculate the velocity for each motor, considering its index, sense of rotation, and velocity, and publish these values over a raster topic. Then the microcontroller read this data from the raster topics and execute the velocity commands for each thrusters. Get data from the sensors and publish this value for raster topics. On the ground station, a raster launch spins off Joy node to publish Joy messages from a Xbox controller and Joy controller, which at a 550 Hz applies of 5% deadband, computes lateral, longitudinal, and vertical commands, and publish in our roster topic called Xbox motor command. Onboard the SP32, onboard SP32 runs a micro-burst client with a connection state machine. Once connected, its motor command fallback function applies a more or less 20 threshold filter and issues low latency PWM signals to each thrusters, keeping end-to-end latency below 20 milliseconds. We conduct the main test. First, underwater computer vision trials calibrating the Pixie camera to detect red and green targets at zero point 0.4 meters depth, achieving a reliable marker tracking in clear water. Second, Real-time teleoperation in a swimming pool validate unstable rusty communication over serial, precise thruster response, sensor data streaming, and overall vehicle maneuverability on remote control. Looking ahead, there are several possibility avenues to extend aquabotics capabilities. Autonomous navigation mapping. We could integrate underwater SLAM pipelines with deep learning based feature iteration to enable the ROV to build its own paths, own maps, and navigate autonomously. Enhancing water quality sensing by adding dissolved oxygen and pH and turbidity sensors. As demonstrated in QV, we could capture richer set of environmental metameters in real time. In seed remediation, deploy of filters, cartridge, or absorbent media could be triggered by onboard sensor threshold, turning Aquabotics into an active water treatment platform. Multi-vehicle swarms. Leveraging decentralized ROS2 communication and a fleet of low-cost ROVs could coordinate grid-based samplings for rapid and large area coverage. Long-term deployment. Integrating energy harvesting models, for example, solar charged buoys, and lower power sleep modes could support multiple weeks mission without human intervention. And the last one is expanded field trials. Finally, testing at turbine or coastal waters would help validate system robustness and sensor fidelity under real world conditions. I gratefully acknowledge the Israel Lab and the RIS Prom and CMU, Dr. Orta Martinez and Nathan Simmerer for their mentorship, and Rachel Borsi and Dr. John Dolan for ongoing support, along with everyone in the CMU community, the RIS Cohort, and our collaborators. Thank you.